model.
Right. Well, yeah, I'm not sure there'll be much great category theory. So last month we had a workshop here on logic symmetry computation. I gave a talk there on certain tests for graph isomorphism. And at the end of that talk, I made a remark linking it to certain, constraint satisfaction problems, and I think made a little jokey reference to Prakash's slogan of categorify. So this talk is really an expansion of that remark into 20 minutes. But this doesn't mean it's a follow-up. You don't need to know anything about the previous talk to follow this. So I know some of you, some number of you were there for that one. I say it's joint work with Pengming Wang. This is not a completed piece of work. It's more some ideas he and I have discussed. Pengming Wang is my PhD student, and he's currently writing up his PhD thesis. So some of this will appear in there, but it doesn't appear as a published piece of work yet. Okay. So we're in the realm of finite model theory. So I'm assuming we have some fixed finite relational vocabulary. So a sequence of relation symbols, each with an associated arity. And I'm going to talk about finite tau structures, meaning structure consists of a finite set and an interpretation for each relation symbol as a relation over the set. Okay.
No constant symbols?
Sorry?
No constants?
Yeah, just what it says. I mean, I don't think it makes it doesn't hurt, but for this purpose, no. For simplicity of exposition, no. Let's put it that way. Okay? As a special case, you can always keep in mind when we have a single relation of binary, in which case our structures are simply finite directed graphs. Okay. Right. We have the notion of homomorphism between structures. So a homomorphism is exactly what you would expect, of course, a function from the universe of A to B, which preserves all the relations. So for any tuple, so boldface A is a tuple. My boldface is working this time. And if it's in a relation, in a particular relation A, its image is in the corresponding interpretation of the relation in B. And isomorphism means the usual, right? There is a bijection, and now this is an if and only if, okay? And of course, I mean, this is simply the category of finite tau structures. And so we can alternatively define isomorphism as the existence of a pair of homomorphisms which are mutually inverse, right? So the compositions give you the identities on the two. Okay, this is, if you will, the motivating picture. Now, from the point of view of algorithmics, these are two rather different problems, right? We have the problem of deciding, given for A and B, whether there exists a homomorphism. This is well-known NP-complete problem. It appears in many different guises, as we've seen over time. I mean, database theory, this is conjunctive query containment. In AI, this goes by the name of the constraint satisfaction problem. So it's NP-complete even for sometimes when you fix the structure B, depending upon which structure, this problem may be NP-complete, but we are thinking of it in general in this form. The problem of deciding, given A and B, whether there's an isomorphism between them, on the other hand, has a rather different status. It's not known to be NP-complete, though it is known to be NP. I mean, it's not known to be NP. And essentially, by Babai's result for graphs, it is essentially in quasi-polynomial time for finite relational structures generally. And therefore, I mean, there's already plenty of evidence that it's not NP-complete, but this we can also take as very strong evidence that this problem is not NP-complete, right? It's looks like it's somewhere in between. Okay. Now, but still, quasi-polynomial time is still pretty bad. In practice, there are lots of algorithms which approximate these two in one way or another, and I want to talk about a particular one. I'm not going to describe the algorithm in detail, but the K-local consistency test is a way of testing for homomorphism. It's not guaranteed to succeed in the sense that it might tell you that these two are consistent, which if they're homomorphic, if there is a homomorphism, there will be, but if they can be consistent even in the absence of a homomorphism. K is an integer parameter here, and the algorithm runs in time n to the order k. So the higher the k, the worse the running time, but the finer the test. So the idea, roughly speaking, k local consistency means I look at a window in A of size k and see if I can map it homomorphically onto B. And I move this window around, seeing whether I can extend the map. But obviously I'm dropping other elements because I never keep a window of size bigger than k. And I move the window around essentially all over A, seeing whether I can always locally extend the homomorphism in B. That's the local consistency test, roughly speaking. It has a connection to logic. Namely, we consider existential positive formulas of first-order logic. So first-order logic, positive means no negations, and existential means only existential quantifiers. And positive doesn't imply the existential. Sorry, that's a remark to Prakash. And we restrict ourselves to using no more than k distinct variables. Okay? For example, I can write down a formula which says in a graph that there exists a k-clique. There exists k elements, pairwise they're distinct. I use this using only k variables. It's only existential, all positive, no negations. But I can't say that there is a k+1 clique. That would require k+1 variables. Okay? On the other hand, look at this. I want to say there's a path of length n for some large n. I can do that just using two variables and no more. Because I say there's a pair of points x1 and x2 with an edge. And then there is some x1, I reuse the variable, which is such that there's an edge from x2 to x1, et cetera, et cetera. So with a long formula, using just two variables, I can do it. Let's see, how am I doing? Just to sort of stress the difference between these two examples. If I have a k+1 clique and a k clique, there's no homomorphism between them. You can't map it homomorphically. But this pair of structures will pass the k local consistency test, because if I look at any window of size k, it maps homomorphically. And I can move the window around, and I can always change the homomorphism to make it work. If I have a path of length n plus 1 and a path of length n, a directed path, again, I can't map it homomorphically. But now I can detect this failure with a simple local consistency check. You start with this, you map it homomorphically anywhere, and then just move this window of length 2 along the path, and you'll eventually run out of space over here, and you've distinguished them. Okay? So here, two local consistency establishes the non-isomorphism. Here, it doesn't. Okay. Now, write this relation to say that, between A and B we have a k local consistency map, or more formally, for any sentence of existential positive logic using only k variables, if it's true in A, it's true in B. Okay? And so algorithmically, the k local consistency test is a test for this relation. Clearly, if I take k to be big enough, say the size of A, then that's equivalent to saying there's a homomorphism. For smaller values of k, this implies it, but not necessarily the other way around. There's a nice characterization of this relation in terms of Pebble Games. I think I've got the date right.
The date's not that, that's your date.
All right. It's 1990?
1995, the paper.
Okay, right.
Yeah.
I was trying to do this from memory. Okay. There's a nice characterization in terms of Pebble Games. So we have a pair of structures A and B, and we have two players called spoiler and duplicator. And we have k pairs of pebbles, which I'll call A1, B1 up to AK, BK. And in this version of the game, spoiler always chooses one of these A's, A1 to AK, and puts it on an element of the structure A. Duplicator has to respond by putting the other element, the matching pebble on an element of B. Okay? And this game can continue for more than k moves, so the pebbles move. Once they're k on, the spoiler has to pick one up and move it somewhere else, etc. At any stage, if the partial map from the pebbled elements of A to the matching pebbled elements of B is not a homomorphism of the induced substructures, spoiler has won. Spoiler has demonstrated the difference. The k-local consistency test has failed. And if duplicator has a strategy to play forever without losing, then the structures pass. So A is A and B are in this relation. Okay. Now, we can think of composing strategies. So if duplicator has a winning strategy between A and B, structures A and B, and a winning strategy between B and C, there's a natural way to compose these winning strategies, right, to get a strategy between A and C. Namely, spoiler, so we have a game between A and C. Duplicator knows winning strategies for both of these. Whenever spoiler plays in A, you choose the response in the strategy over here. Now treat that as a spoiler move. Choose the response of duplicator in C and take that as a response to the original move in A. That's a nice informal description. Formalizing it, I mean, it's not too difficult, but I'm just going to try and do this a bit carefully. So I'm going to define a strategy for this game as a set of pairs. So think of these pairs as possible positions in the game. So they are L tuples of elements for some value of L between 0 and k. Okay, the value of L varies from tuple to tuple, right? What I mean is L is not fixed for H. So, and we have certain properties, namely it's sort of downward closed. Whenever you have a pair in H, eliminating corresponding elements of the tuple still gives you a pair in H. Okay, this means that basically you can remove a pair of pebbles in the game. And then the extension property, if you have a pair of tuples of length strictly less than k, then there's an extension, namely a function from A to B, so that the extension of the tuple with A and B with f of A gives you all of them are tuples in H. Okay, now this, when I write the definition down, it seems slightly unsatisfactory because I'm calling this a strategy, but doesn't give you a strategy in the way we usually think of it, because I'm not saying this function's unique, right? So it doesn't tell you what duplicator has to do. It just says there is something duplicator can do. So it's not a strategy in this sense. So if we try and say, actually, we could try and formalize the notion of strategy as something which, for any position, gives you a particular function. That leads us into a bit of a difficulty, which is maybe best explained in this picture. So suppose we have a fixed strategy, namely for any position here, a function which maps to this, and for any position between B and C, a function that gives us the next move. It's not clear how you compose those, because given a position between A and C, there are many ways you could factor it into a position between AB and BC. And those factors could give you different functions. Okay? And there's nothing in the definition here that enforces consistency of those different functions. So instead we define a strategy to just be a set of positions with these closure properties. And this guarantees that in some sense it contains a strategy. Right? That there is somewhere in there a function. Okay. And the point of this is this now allows a nice notion of composition. We also have a notion of identity strategy, so we've got ourselves a category. Okay. I will say, I'll call a strategy injective if it satisfies this, and in condition 2, you can always choose the function f to be injective. Okay? And I'll sometimes denote that I didn't put it on this slide with a little subscript on this relation symbol for injective function. Okay, with that, we get a nice little thing we can prove. So the following are equivalent for any pair of structures. This is the usual notion of isomorphism in the category I've just defined, right? So there's a pair of strategies which are mutually inverse. This is equivalent to simply a pair of injective strategies in both directions. Okay? And this is equivalent to the existence of a bijective strategy from A to B. Okay? And the reason this is nice is because this number 3 condition is something sort of which arises very naturally in an entirely different way. This is essentially a winning condition for something that's called the bijection game, which was introduced by Hella. And it was introduced by Hella as a characterization for a certain counting logic. Okay, so Hella's bijection game characterizes a certain equivalence relation, which I call K equivalence, which says that two structures can't be distinguished by any sentence of K variable first order logic with counting quantifiers. Now this is sort of, as I said, was kind of independent interest. And Hella introduced a bijection game for analyzing this, which was used for analyzing certain fixed point logics with counting. Here, this equivalence just falls out as the notion of isomorphism in the category of strategies we defined. And this equivalence relation turns out to have many independent characterizations. I mentioned bijection games. I mentioned these, counting quantifiers logic. It has an entirely combinatorial characterization, which is well known from Babai's work on isomorphism. Basically, this K equivalence for a pair of graphs is the same as saying that they can't be distinguished by what's called the K-1 dimensional Weisweiler-Lehmann method, which is a well-studied approximation of graph isomorphism. Right? Again, it gives you an algorithm for an approximation of graph isomorphism for any fixed value of K. And well, we know that there's no fixed value of K for which it gives you all of isomorphism. That's the famous Seyfer-Immermann result. Okay. Okay. So this, so far, is kind of a nice observation that defining this K-local consistency in terms of strategies which we can compose allows this nice, independently well-studied notion of equivalence to fall out. What can we do with this? Well, we don't quite know yet. One thing we looked at, now essentially looking at classically what we know about the category of structures under homomorphisms, what can we reproduce in this framework? We looked at the notion of a core. So a structure is called a core if it has no proper retract, right? So no proper substructure onto which it maps homomorphically. We know that every structure contains a core, right? And moreover, it's unique up to isomorphism. Okay. Every finite structure, yeah. Very first slide, all my structures are finite. Okay. So every structure has a core, and it's unique up to isomorphism. And now we can reproduce this. What does this mean in the category we have just defined? So we say that A prime is a K core of A if it satisfies the following conditions. It maps K locally to A maps K locally to A prime. Right? So we've replaced the homomorphism condition with K local consistency. What happens to the substructure condition? Well, to say that A prime is a substructure of A is just to say that there's an injective homomorphism from A to A. So this becomes A prime maps injectively K locally into A. And we want a minimality condition, which turns into this. For any structure to which A maps K locally, and which maps injectively K locally into B, then A prime maps injectively K locally into B. That's the minimality condition. And then we can show that every structure has a K core, and it's unique up to CK equivalence, or K equivalence, right? The bijective games. I think there's a lot more you could do just in terms of looking at natural properties in this category of homomorphisms and reproducing them here.
Would it be the same to say that A prime is a retract?
The first condition, exactly, yes. No, I did say that verbally. It's not on the slide, but I did say retract. Yes. Okay. Now, when we started doing these definitions, we were after something we would like to prove, which we still don't know how to prove. So I'll end with a few questions. This is, I mean, for those of you who were around at the beginning of the semester, Peng-Ming gave a talk about an open preservation theorem he'd like to prove. This is a version of that statement, and you may not recognize it as such. If we have a class of finite structures which is closed under K-equivalence and closed under homomorphisms, is it closed under K-local consistency? Or, let's say, K-prime for some K-prime. Okay? This is a reformulation of the preservation theorem that Peng-Ming Wang's. And this was actually what we were motivated by. We were looking at this in formulating this, but so far we don't know how to use this reformulation to get anywhere with this. The other sorts of things we're looking at, and this is what I mentioned at the end of my talk in the symmetry workshop. Well, this is sort of a pair of dual questions. We have other ways of approximating homomorphism other than K-local consistency. There are lots of sort of these algebraic constraint satisfaction algorithms. What sort of useful isomorphism tests could you extract from those? And conversely, there's lots of isomorphism tests, unlike the Weisfeiler-Lehmann, based on sort of group theoretic algorithms, or like the ones I talked about before in the last workshop, about based on invertible linear maps. And again, there seems to be maybe a useful notion of homomorphism one could extract, for which that is the right notion of isomorphism. I'll stop here.
Thank you very much.
Could you please go back to the slide where you first showed the strategy with the function in there with the two characters?
Yeah, here.
Yeah. Okay, now in the second condition there you have f of a
Yes.
at the end.
Right. I'm extending the tuple A with the element A and the tuple B with the element f of A.
But shouldn't the function a depend on more than just a?
Well, I'm saying for every pair there is a function. So,
Oh, it's separate for each pair.
yes.
So it's
Okay, so it's the same way. Okay.
Yeah.
Sorry.
Okay.
Other questions?
Josh.
In the 70s, Kicker had the notion of core. Are you aware? You must be aware. In infinite model theory, I was wondering whether this is...
The core as he defined it may not exist on infinite graphs. Take just a straight line.
Yeah.
No, I know. Kicker didn't prove it exists always, but there was an...
No, okay, I don't know that notion. Be
careful about the name.
No, but this name comes from.
Graph theorists have claimed
Yeah.
it 30 years ago.
This is from, well, certainly in Helen Neshetel's book, which is from 1990. It's
The paper by Helen Neshetel is from the 80s.
80s. Yes, okay. So,
Almost equally. Anuj, what about computing the K-core? Computing the core is empty hard. What about computing the K-core?
So I don't know. The thing about the K-core is that unlike the K-core doesn't have to be a substructure of A. Right? We've replaced the substructure condition with this. But I suppose you could actually, because of the injectivity condition, you know that it's no bigger than A, so it's going to be an NP, that's for sure.
But the question is because...
Hardness, I don't know.
All right. Thank you very much.